So the Mark III is all built and ready to go, but before I get started on that, I want to talk a little bit more about the TLC272 that I'll be using. So here I have the data sheets, and it turns out, just like on any other data sheet, the front page numbers are a little bit misleading. So you can see here the maximum input offset voltage of 500 microvolts. Well, that's fantastic, right? That's half a millivolt. That's much better than the LM324. But first of all, that's only at 25 degrees C, and that's not a problem. We're at room temperature. It's only for VDD equals 5 volts. Well, we're at 9 volts, but that's not too much different. Oh, and by the way, that's also for a completely different part. That's for the TLC277, which is also included in this data sheet, but I have the TLC272. So for the numbers that I'm interested in, I have to go into the data sheet. So here we have VDD equals 10 volts, that's closer to what I'm using. And here's the input offset voltage for the TLC277, and also 3 different types of TLC272. I have the 272C. So if I look over here, I can see that the maximum input offset voltage is actually 10 millivolts instead of the half a millivolt. And that's even worse than the LM324. I still think this is a much better part to use than the LM324, if only because of these input bias currents. The maximum input bias current, input offset current, is 60 picoamps, which is 2 or 3 orders of magnitude smaller than the LM324's bias current. And the average input bias current is about 2 orders of magnitude smaller than that. The problem with the LM324's much larger bias current was that it would run through my body and create a voltage drop, which was unpredictable and uncontrollable. Here I only have to worry about this large input offset voltage, but I do have a worst case number for that. I know it will never be larger than 10 millivolts. So I can come up with a worst possible case for my circuit and sort of design around that. Whereas with the LM324, I couldn't come up with a worst case for that to design around because my skin didn't come with data sheets. So one more thing before I start it up. Here's the circuit for the Mark III. If you remember, I have 2 op amps at the input, at the front end, and each of these could have up to 10 millivolts of input offset voltage at them. So a worst case for the offset voltage between the 2 inputs there would be 20 millivolts. And that could either be positive 20 millivolts or negative 20 millivolts. So the DC offset at the input, just from the offset voltage of the op amps, could be within a 40 millivolt range. Now the output of the LM324 that I'm using for the back end can't even swing all the way up to the positive supply rail, and the battery's getting kind of low, so let's say the output range is about 6 volts. So in order to keep the 40 millivolt range at the input within the 6 volt range at the output, I have to keep the gain at or below 150. So I knocked that down to 100 just to give it a little bit more wiggle room. And that's where I came up with these resistor values that just give the front end a gain of 100, and the back end has a gain of 1. Then you can see another couple op amps in here. This one here is just a voltage follower that's splitting the supply. So this is my reference for the entire circuit. It's basically a ground, and then you have plus 4.5 volts and minus 4.5 volts. This other op amp here is actually my DC offset correction. It's feeding into the same part of the back end that I had the voltage follower and variable resistor at last time. So this op amp is set up as an integrator, which is part of this control loop here that automatically adjusts the DC offset for me. So it looks at the output voltage of the circuit and compares it to this reference voltage here. And if the output voltage is higher than the reference voltage, then the output voltage will steadily fall over time. And if the output voltage is lower than the reference voltage, then the output will rise over time. So if the voltage at the output is too high because of a DC offset, this output here will steadily fall over time and subtract off some voltage from it until eventually it reaches the same voltage as this reference, and then the output will stop changing and stay where it's at. This DC offset correction control loop was also used in another homemade ECG project I found online, which I'll link to in the description down there. And here the design is actually a bit different than what I'm using right now. It's the same type of front end, and then here's the back end over here, and the DC offset correction actually happens in between the front end and back end. It's sort of an interesting design, and I might go into that later. And I might actually use a circuit sort of like that eventually, so I'll keep that around. Alright, now let's turn it on and get it working. I thought it might be interesting to show the DC offset correction loop in action before plugging it in for realsies. So here the multimeter is plugged into the output of the integrator, which shows us how much DC offset that it's subtracting from the output. So when I poke around on these electrodes, I can sort of change the DC offset around quite a bit, and that shows what it's subtracting off of the output. Then when we plug the multimeter into the output of the whole circuit, after the DC offset has been subtracted off, see it stays mostly around 0. When we change the DC offset again by poking around with these electrodes, you can see that even when it jumps up, it eventually tracks back out to 0, which is exactly what I want. Alright, so I'm ready to go now. It's really not necessary to have the multimeter in the shot anymore since the DC offset is taken care of. But I'm still going to take a video of the monitor instead of using a screen recorder because I'm just too lazy to get a screen recorder. You'll just have to deal with this. I changed the positioning of the electrodes a little bit, so I have one in the middle of my chest, one just underneath my left armpit, and then the ground electrode is just sort of down and off to the side a little bit. So I just sort of plugged this in and started recording. I'll stop it right here and see what we got. I could see some little blips in there. Let's go ahead and grab this and amplify it. So that's 36.9 dB, so about 40 dB, which is a voltage gain of 100. And there it is. This gave me exactly no trouble at all. No messing about with the electrodes, trying to get things just right. It just sort of worked. Except for that. That didn't just work. This over here, that just worked. Alright, now I have all this noise on there, and that's the next thing to figure out. Let's go ahead and play that out of the speakers and see what it sounds like.
Couple of months hurting each other, all of a sudden they're irritating like crazy after a couple of years. So it's one of the reasons why I'm also
Alright. Sounds like this thing is an ECG/radio. It would be interesting to know whether or not that's coming from my circuit or just being picked up by the sound card. So let's turn this off and just unplug it and start recording nothing. Let's go ahead and stop that. Let's amplify this by the same amount. Let's call it 40 dB. Okay. Let's try and play this out of the speakers. That's nothing. Let's amplify it some more just to see what it is. Ooh. Alright, so it's pretty clear that the noise I was picking up on the heartbeat signal was not coming from the cable going into the computer, but actually being picked up by my circuit. But I'm definitely on the right track. The DC offset problem is solved, I think. I've had no problems with it so far. Since I had to lower the gain of my in-amp down to 100, and then I had to do another voltage gain of 100 after I recorded, I might put another amplifier after the back end, after the DC offset has been removed, just to give it another voltage gain of 100, and that way I won't have to amplify after I record it. But yeah, in the next video, I'll try to remove some of the noise from my heartbeat signal and get a cleaner output.